Now, fatigue is a decline in the muscle's contraction or a decline in a muscle's ability to maintain its contraction after repeated stimulus over time. So basically, if you continually excite this muscle, you increase the frequency of contraction or of innervating this muscle. After a while, we're going to lose the amount of tension and force, and this is called muscle fatigue. Okay, now in terms of high intensity exercise, these are some of the reasons that kind of explain why we see muscle fatigue in these types of fibers. So they're more glycolytic fibers. And so because they're more glycolytic, they have that anaerobic glycolysis going on. And so they build up lactate. Now the problem with lactate is that it is acidic, it's an acid. And so it changes the pH inside the cell. This deactivates some of those glycolytic enzymes that we need for anaerobic glycolysis, okay? So having that lactic acid build up is what sort of contributes to the fatigue that we see in glycolytic fibers. Also, there are strong contractions. What did we say about the fiber types in these, the fiber diameter in these types of fibers? It's bigger. So when these muscles contract, like these are bigger muscles, when they contract, they actually compress the blood vessels that are around them. And that can sometimes cut off their blood flow. That also contributes to fatigue, okay? We also see neuromuscular fatigue, which is basically because these, again, muscles are bigger here. We need more calcium, we need more neurotransmitter at the neuromuscular junction. And so after a while, we can deplete that neurotransmitter and we can generate fatigue that way, right? If we run out of or deplete our neurotransmitter sources. Also, we have altered enzyme activity, again, which is due to that buildup of lactic acid, right? We denature, remember those enzymes are nothing but proteins. And in an acidic environment, we can denature those proteins and we can lose function that way. Now, the recovery time with high intensity exercise is going to be very quick, right? So it's going to be much quicker. And again, I want you to think about those two parallels in your mind, that slow long distance runner and that heavy lifter, bodybuilder or sprinter, okay? The bodybuilder is going to recover a little bit easier than the slow long distance runner, okay? And that's because it takes less time for fatigue to build up with these types of high intensity exercise. He's going to feel that burn right away. So it's going to happen more quickly, but it's also going to resolve more quickly, okay? Let's look at low intensity exercise and what contributes to fatigue here. So the depletion of our glycogen stores is thought to be contributing to fatigue in these types of fibers. And although it seems counterintuitive, right, these fibers are mainly relying on oxidative phosphorylation. Oxidative phosphorylation still requires glucose as one of its byproducts, right? To get down to the ETC, we still need glucose as our main substrate. So if we have longer, slower, more sustained contractions with this type of low intensity exercise, we run the risk of depleting our glycogen stores, depleting our glucose stores, okay? So that's what sort of contributes to the fatigue that we see here. Now, this is going to take a much longer time to recover because it takes a much longer time to sort of occur, right? Think about, again, that long distance runner. He's probably going to run a really long, maybe a 5K, and his fatigue will take a longer time to sort of set in, but it may take 2 or 3 days to actually resolve that fatigue, okay? I also want to point out the psychological component to fatigue. So basically, we talk about muscles' inherent ability to sort of lose tension or lose force, but there is a psychological component. There is this will, the human willpower. This is seen a lot in athletes, right? So in the face of decreasing muscle performance or decreasing muscle tension, we have this psychological will to sort of keep pressing on, okay? That's not seen in other animals and other species, but it certainly is seen in humans. And it's a really important component to understanding fatigue, okay? All right, so let's look at this illustration here, which kind of helps us understand how fatigue occurs. So this is a normal rate of isometric contraction happening here, okay? And as you can see, we have a moderate frequency, right? A moderate amount or moderate rate of innervation or action potentials being fired here. But if we increase that frequency, what we see is that the force generation, the tension generation begins to drop off. And this is what we call fatigue. So we're stimulating that muscle too quickly, right? The frequency is just too fast. And so after a while, we start to pay for that. The muscle loses its ability to generate or to sustain force generation. And over time, if we further increase that frequency, we can see that we get tetanus. We spoke about tetanus, where we have that fused contraction, and then we just lose tension or force altogether, okay? So basically, you're lifting something heavy, and then your muscles just give out. That is where fatigue comes in with tetanus or sustained tetanic contractions. Now, what we see here with fatigue as well is that even after a period of rest, we become fatigued, or the muscle becomes fatigued much more quickly than the initial rate of fatigue. So this is also a component to fatigue, that even after a bit of rest, this muscle fatigues the next time even more quickly until it fully recuperates or fully resolves, okay? All right, any questions so far? Any questions? Okay. Now, let's talk about some of the long-term responses to muscle with different types of exercise. And I'll really just sort of summarize what we changed. So I mentioned earlier that we can change the source of ATP production, the main source of ATP production with muscle. So doing lots of aerobic exercises like walking, jogging, swimming will condition our muscles to rely more heavily on oxidative phosphorylation. And so this is why we do those types of exercises. We can generate more blood flow because we get smaller diameter of muscle. We have more fast glycolytic fibers becoming oxidative fibers, right? More reliant on oxidative phosphorylation. And we can increase the amount and the number of mitochondria. So again, this is the source of ATP for these types of fibers. So it makes sense that we'd see lots of mitochondria, lots of myoglobin. We also increase the number of capillaries that are surrounding these muscle fibers. And this is why this type of exercise is good for your heart, right? It's going to increase blood flow because it's going to decrease that fiber diameter, increase more capillaries coming into those muscles, which is including the heart. And that's more of a healthy, sustainable environment for our muscles and for tissues and blood vessels. In high intensity exercise, right, the craze is hit, right, high intensity training, this is how we generate our muscles to rely more heavily on fast glycolytic, or on anaerobic glycolysis, okay? So we generate more fast glycolytic fibers, and they're gonna decrease the number and size of mitochondria, they're gonna decrease myoglobin, they're going to increase their fiber diameter. This is how we bulk up muscle, by lifting heavy, right? That high intensity training is what gives us that fiber diameter. But we're also going to see a reduced resistance to fatigue, okay? And so this is how muscle responds long-term to different types of exercises. Aerobic exercises, which are more low-intensity exercises, versus high-intensity exercises, which are more strenuous, more vigorous, such as heavy lifting and sprinting and so on. All right, let's speak about atrophy a little bit. Now, atrophy is simply the loss of muscle fiber. The loss of muscle fibers, the loss of myofibrils in terms of those subcellular components. So basically, if we don't use a muscle, right, let's say we worked out, we got really bulky, right, bulked up our muscles, and then we stopped working out for a sustained period of time, the muscle would lose some of its myofibrils. Just like when we worked out, it gained myofibrils. If you stop working out or if you stop using the muscle, you lose some of those myofibrils. This is called disuse atrophy. We see this a lot with nerve injuries. So if you're not innervating a muscle, right, if you have some type of paralysis, the muscles will eventually wither away, they will atrophy, they will become very sort of paper thin. And that's simply because we're not using them, we're not exciting them, and you just lose the fibers, we lose that density, that fiber diameter. There's also, which are muscular dystrophies, right? Muscular dystrophies, again, problems at the neuromuscular junction, be it acetylcholine release or receptor problems like myasthenia gravis. And again, because we're not exciting that muscle as often as we should, we're not using it, we see that atrophy from disuse.